This presentation is an introduction to the CE-Chirp family of acoustic stimuli that are developed to increase response amplitude and this way reduce test time when doing threshold assessments with ABR or ASSR. When doing ABR or ASSR, we always talk about how noise is really the big challenge. However, the question is if indeed it is the noise that is our problem, or if it is not rather the response to noise ratio. If we look at response to noise ratio, then we can see how by driving down the noise, we will improve the response to noise ratio and thus have easier access to look at clean waveforms. And the problem in reducing noise is, as we all know, that it takes a lot of time. So, the alternative to reduce noise to very low limits is to increase response amplitude. But is that possible? Well, that is where the CE-Chirp is created to give us larger response amplitudes. So, to achieve such larger response amplitudes, we have to look at synchronization of the nerve firings. And this has always been the issue when doing electrophysiological testing. How can we best possible synchronize all the fibers involved in a particular response? When doing so, there is a huge problem that until recently has been overlooked, and that is the way the Cochlear works, because that has crucial effect on synchronization. We all know the typical stimulus used for ABR, the click. The beauty of the click is that it has all frequencies in a very short time window, typically 100 microseconds. So within that short period of time, we present all frequencies involved and kind of think, well, then all the nerve fibers must fire at the same time because all frequencies are present at the same time. But that is where we actually are mistaken, because inside the cochlear we have the basilar membrane and we have a travel time for sound when it arrives into the cochlear. If we look at this picture, then over here we have the stapes, and the click is introduced into the cochlear through a movement of the stapes. The highest frequency components within the click, they will excite the basilar membrane right here at the very beginning, and immediately the nerves attached to the hair cells involved in this basilar part or basal part of the basilar membrane will start responding. Medium to low frequencies are later up towards apex in the cochlear, and it takes travel time to move from the basal part towards the apical part of the cochlear. So it may take like 10 milliseconds or so for the lowest frequencies to actually arrive at their place on the basilar membrane and excite it, and thus provide a neural response from this part of the cochlear. If we then look at the click stimulus, it provides us this kind of ABR. We have a time scale down here with 0 milliseconds, so that is where our recording typically begins, and this is where we present our click in traditional systems. And we get our ABR response, which is here around, in this case, around 6 milliseconds for wave 5 peak, and a response is present. If we analyze this stimulus in a little bit of detail, then we can take the 4 kilohertz octave band or narrow band that is part of the click, but only an individual part, not the entire click. The 4 kilohertz narrow band octave will look like that, and the 2 kilohertz narrow band will look like that. The same with 1K and 500 Hertz. Altogether, these four make up this particular click. The interesting thing is how we have responses associated with these individual parts of the click. Now, on your ABR screen, of course, you do not see that response part which only is caused by the 4 kilohertz octave band, which would be that. Neither do you see the response part here that is caused by only the 2 kilohertz octave band, and so forth here, but you do see the sum, and this is the sum. But by analyzing it the way we have done here, we can see how these are actually not too well synchronized as far as providing maximum response down here when we add them together. And this is what we will try to look at with the new stimulus. Because if we try to look just at this particular component of the stimulus and its response, then it is clear that if we move the point in time on the time scale where we present our stimulus, then of course the response would move to the exact same degree. If we take this one and we move that a little bit more, so instead of presenting it here, we would present it there, then the associated response would move by a similar amount. The same for 1K, we could move that quite a lot, which would move the response quite a lot, and for 500 Hertz even more. This could be interesting, so let's indeed try that. Let's try to create a stimulus that has subcomponents that are indeed positioned in this way in time. When we do that, we get a stimulus that in technical terms is called a chirp. And it looks like that. So this is the sum of such parts of the stimulus. These are the associated response components, and if we add those together, we will see what it gets down here. Now, just for comparison, I have added here the click response. So this is if we do not change this in time, which changes these in time. This is the click response, but the chirp response looks like this. Let's go back. Click response and chirp response. And this is achieved not by louder stimulation, it is achieved only by reshuffling the time components of our stimulus. That is how we have created the CE-Chirp stimulus for ABR or ASSR. It looks like this, and we have the low frequencies coming into the ear a little bit sooner than the high frequencies. This is different from the click where they all arrive at the same time. Now, to which degree should we indeed have the low frequencies get a head start into the Cochlear? Well, there are models that describe this, and there are a variety of models here, and the trick in getting really good improvements in response amplitude by using chirps is, of course, to find the right delay model. It is very crucial for optimum response. And that is where we have researched the CE-Chirp for about 10 years now and arrived at the optimum delay model for the chirp stimulus and call that the CE-Chirp. Here comes an animation of the CE-Chirp to show you how it actually works in the ear and in the auditory neural pathway. In this animation, we have on this side our Cochlear with the basilar membrane, and then we have the neural system, or part of the neural system, that leads to the brainstem. And we have the acoustic stimulus down here that we can put into the cochlear. Over on this side, we have the responses. And what we will show here is the response components associated with, for example, the 8 kilohertz part of a click, the 4 kilohertz part of a click, and so forth. Now, these are subcomponents, as we saw before, that are not really visible on your ABR screen, because on your ABR screen you will only see the sum of these activities, and we will show the sum associated with these subcomponents up here. So this is how the layout of this little animation is. When I start running my system here, we can see this is time that moves, and now I'm presenting my click, and we can see how these different colored circles are each representing a particular frequency range. So when I move time slowly here, we can see how this one, representing a very high frequency, has already stimulated the basilar membrane to activate a response now traveling up through the neural pathway towards the brainstem. These frequencies are still traveling inside the cochlear. And we can run time here slowly. And for example, at this point in time, the highest frequency part of the stimulus is almost at the brainstem, whereas the lowest part of our click stimulus is still traveling inside the cochlear. It has not started to create a response on the basilar membrane and have anything happening in the nerve fibers associated with this low frequency. Let's take it a little step further here. So, if we stop time here, we can see that the highest frequency has now arrived at the brainstem, and we can see over here on the response part of things how the 8K response associated with the 8K stimulus has actually created a little peak in response. Whereas, for example, the lowest part has not done anything as far as contributing to the overall response yet. But I can continue my playing with time here. And if we stop the recording at this point in time, we can see how the response associated with the highest frequency is almost over and done now, where these frequencies are still creating some level of response, and the lowest frequency part is starting to respond. And when we run it all the way to the end, we see how we do get responses from all the different frequency parts, but they are not really aligned. And when they are summed up, which they always are in your ABR system, what you see is this, our typical ABR response. All right, this is how click works. Let's try to see how the CE-Chirp works. Here comes the CE-Chirp. Very different stimulus in the time domain compared to the click. And when I start playing with time here, the low frequency part is introduced into the cochlear much sooner than any of the others. Here comes slightly higher frequencies into the cochlear as time passes by down here. And of course the trick is to have the chirp in such a way that all these different frequency components arrive at their specific point on the basilar membrane at the same time and excites the basilar membrane at the exact same time, travels up through the neural pathway synchronized, and arrives at the brainstem synchronized. If we look at the response associated with such a stimulus, then see how the high and towards lower frequencies, all of these are indeed now synchronized. And the sum is looking quite different from that of the click. Beautiful, isn't it? All the positive going peaks are synchronized to create a very large positive deflection on the waveform, and all the negative going parts of the response are also synchronized to produce a very large negative going component in your response. And we get this very, very nicely defined large response. Actually, up to 2 times response amplitude is the benefit of the CE-Chirp compared to the click. Let us look at how the CE-Chirp and the click response waveforms look. So this is the same patient, it is in the same session, and over here we have the CE-Chirp responses, and over here we have the click responses. We can see how for 80 dB we get a nice waveform here, and also we get a nice waveform for click. We can also see that the click waveform looks more like we're used to it from when looking at clicks. We have clearly identified 1, 3, and 5 here, where they look a little bit different when using the chirp, because the chirp, as we have discussed, is a little bit different in the time domain. Also, at this very loud stimulation intensity, the increase in response amplitude is not as pronounced as it is when we go down towards lower levels of stimulation. For example, look at this 60 dB response for the CE-Chirp and compare that to the 60 dB response amplitude for the click. This is much nicer, pronounced, and also larger in response amplitude. And that is even more so when we go down to 40 dB. 40 dB CE-Chirp, 40 dB click. 20 dB CE-Chirp, very easy to see. 20 dB click. We can see how the smearing in time is quite pronounced here, which makes it more difficult to see the response compared to here. Even at 10 dB, we do see an improvement in this patient. And the stimulation levels, as mentioned previously, are the same. They are in dB NHL in both cases. Frequency-specific stimuli are also possible using this kind of CE-Chirp technology. And this is very important because with the frequency-specific CE-Chirps that are called narrowband CE-Chirps or octave band CE-Chirps, then you can get an actual audiogram by frequency-specific stimuli, which is so important to take advantage of modern hearing aids and achieve an estimated audiogram that can really do benefit to the fitting of modern hearing aids to the hearing impaired children. So what do we do for frequency-specific stimuli? Well, for 500 Hertz we have a stimulus that has this kind of spectrum. And if we look at the stimulus in the time domain, it has the same chirp features of having the lower frequencies appear prior to the higher frequencies. So within the band of stimulation, we do synchronize all the associated nerve fibers. The same is true for the 1 kHz narrowband CE-Chirp stimulus. Spectrum-wise, it looks like this. It stimulates this part of the basilar membrane, and this is how it looks in the time domain. And for 2K and 4K. Let us look at how the narrowband CE-Chirps and the 1 kHz tone bursts compare as far as waveform. Here we have the 1 kHz narrowband CE-Chirp. It's the same patient as is recorded over here. Let's look at, for example, 60 dB with the 1 kHz narrowband chirp compared to 60 dB with 1 kHz tone burst. Much better pronounced response, amplitude and morphology on this side. The same is true for 40 dB compared to here, and 20 dB compared to here. So the rather difficult task of doing frequency-specific ABR is made a lot easier with these types of waveforms compared to the traditional tone burst waveforms. Also note that the latencies of the narrowband CE-Chirps is shorter here compared to here. That is due to the way we have positioned the CE-Chirp in the time domain and has actually nothing to do with the travel time inside the cochlear. So there are normative data for the latencies for narrowband CE-Chirps to tell you where to look for the response peaks. What we have discussed here is actually the culmination of more than 10 years of research by Klaus Elberling and others. Klaus Elberling, the name also reveals why it is called the CE-Chirp, because that is Klaus Elberling, who has been the driving force and done most of the research in this area. The implementation of this technology has started already back in 2006, where the Eclipse ASSR system from Introacoustics started using these types of frequency-specific narrowband CE-Chirps, and was one of the reasons why test time with this particular product was approximately 50% of traditional ASSR systems. Then a few years later we introduced the stimuli in traditional ABR, both as full frequency stimuli and as narrowband frequency specific stimuli. And in 2011 we have introduced the ABR infant screener in our Titan platform. Thank you very much for listening in on this presentation on the new technology involved in stimuli for evoked potentials that provides larger response amplitudes and thus saves you test time. Thank you very much.